Today we are learning about Lesson 3-2, Linear Functions. Don't forget to write your name, date, and period at the top of your paper. So we have here our objectives. Students will be able to write and evaluate linear functions using function notation. We will also be able to graph a linear function and relate the domain of the function to its graph. We will also interpret functions represented by graphs, tables, verbal descriptions, and function notation in terms of a context. As for the vocabulary, we have domain, element, range, functions, and linear function. The essential understanding is that linear functions can be represented in multiple ways, using words, tables, graph, and rules. The output of the function fx can be read as f of x. It means that f is a function of the input variable x. And we have here in the bottom, example 1, evaluate functions in function notation. The first problem states evaluates each function for x equals 4. So our input variable our input variable is the variable x, which is 4. And part A states g of x equals minus 2x minus 3. So we'll have to put in, well, first we can copy down the function. And now we will input that variable and what it equals to into our function. So this means that in place of x, we will put in the number 4. And that process is basically saying plug in the number. Now we solve for the right side. Minus 2 times 4 is minus 8. And minus 3, copy that down. Minus 8 and minus 3 equals minus 11. Now we have g of 4 equals minus 11. So part B states that h of x equals 7x plus 15. And now we will input the variable, or we will input the number 4 for our variable x. So first, copy the function down, h of x equals 7x plus 15, and put our number, which is h of 4. And that means we'll put in 4 for our x plus 15. 7 times 4 is 28 plus 15, h equals 15. And now we will have h of 4 equals, and do that in our head, 43. h of 4 equals 43. Now we will be writing a linear function rule. So write a linear function for the data in each table using function notation. Now in part A, we have the table x, y, and we have the inputs 1, 2, 3, 4 in our x values, and 6.5, 13, 19.5, and 26 in our y values. Now, the first step in writing a linear function is to look at the pattern between the x values and the y values. So in the x values, we notice that whenever we go from 1 to 2, 3, and to 4, we add by 1. So that's pretty easy. And now from 6.5, from 13, 6.5 to 13, and 13 to 19.5, 19.5 to 26, we notice that if we subtract it from one another, put 0 here, and we solve for that, that is adding by 6.5. From 6.5 to 13, we added by 6.5. So we double the first value. And from 13 to 19.5, we also know that we added by 6.5. And I'm pretty sure that if we take the value, the difference between 26 and 19.5, we would also get, to make sure, we would also get 6.5. So now we know that the pattern in our x values is that we added by 1s. And in our y values, we added by 6.5. What we really need is the pattern happening in the y values, because this is the rate of change. This means that it is the slope, or the m, of our function. And our function can be written in f of x equals mx plus b. Now you guys might notice that this is kind of the same to the slope-intercept form, which is y equals mx plus b. And now we go back to our rate of change, and we plug that into our function form. So m would be 6.5, and we copy down the rest, plus x plus b. And don't forget the front, f of x. Now we will need to solve for the b, or the y-intercept. And we can do this by plugging in one of the x values. So we could take 2, the x value of 2, and input that into our function. So f of 2 equals 6.5 2 times 2 plus b. Now 6.5 times 2 is 13 plus b, and we know that if we have f of 2, we can look here in our xy table, or input and output table, that f of 2 is 13. And when we solve for b, we subtract 13 from this side and subtract 13 on the other side. These two cancel out, and these two becomes a 0 on the left hand side. So 0 equals b. With b equaling to 0, we can just say that in our function, linear function, that f of x equals to just 6.5x. And that's our linear function for part A. Now we also have part B. In part B, we have the x and y values. X is 1, 2, 3, 4. And from here, we know that patterns go up by ones. And in the bottom are y values from 1, 4, 7, and 10. We can just deduct 4 minus 1 is 3. 7 minus 4 is also 3. And 10 minus 7 is 3. So that one's pretty easy to spot, but we go up by 3s. Therefore, our rate of change is 3. Always remember that rate of change can be taken from the pattern in our y values. So m equals 3. Now we will write down our function. Form f of x equals mx plus b. And we know that our m equals 3. Copy down the rest, x plus b, and of course f of x. And when we solve for b, remember that we will just input any variables from our x values. So we can take, for example, 4. F of 4 equals 3 times 4, when we plug that in, plus b. Solve for that. Back in our table, f of 4 has the output 10. 4 times 3 is 12 plus b. And now we will subtract 12 from this side because we are solving for b, minus 12 on the other side also. Now 10 minus 12 is negative 2 equals b. And so with all of this, we now have our m and we now have our b. And we will go back to our function form and just plug in those numbers. So m is 3x, and of course we have plus, and then b was negative 2. And we can simplify this function and just state that f of x equals 3x minus 2, because the negative sign in 2 cancels the positive sign. And there we go. We now have our linear function from our data table.